In this video, I expect to start a kind of loose, ongoing series of mathematics and music. These videos, separate from the others, will not have as definite an order or structure to them, but please feel free to watch them. You'll very likely uncover something that you'll find surprising or new to you. I'll be using a program called Cam Studio, which you can see in the upper left corner, along with Microsoft PowerPoint, at least for now. And even continuing in the future, I'll have probably a central theme to discuss for each video in this playlist. Now, overall, my personal argument, as I'll say as I load this up, my personal argument is really that mathematics and music are easily relatable. One might say, in fact, that they are essentially one and the same. But without further ado, here it is, musical frameworks which could surprise you. So now, in terms of the history, there are really two very reliable sources which I'd like to cite for this part of it. Essentially, in terms of content, Pythagoras, whom you see right here, the ancient Greek mathematician, he was arguably the first person, or at least one of the famous mathematicians, to begin studying music, really, and its relation to mathematics. We'll get to that in a moment. There are various sources, various stories about Pythagoras and how he really came to study music and everything, and harmonies and things like that. But in terms of history, we have two main sources, which I'd like to cite. First, there's Professor Paul Coulter, who has several degrees, and he taught for more than 20 years, actually, at the Vermont Technical College. He's really a very nice source. And furthermore, there's an Oxford professor, Marcus du Sautoy, who, by the way, is the author of a very good mathematical book called The Music of the Primes, Searching to Solve the Greatest Mystery in Mathematics. And I very much recommend that book. I actually bought that, and it's quite good. I almost finished it. I actually got to I think one of the final chapters, and then I actually stopped there because it got a bit complicated with the quantum mechanics. But still, yes, very good book. I seriously recommend it, really, for anyone. It's well written, and it's just about mathematics. It can really get you interested in really the history of mathematics and the people involved, and that's a good way to teach mathematics, in my opinion. Evidently, Marcus du Sautoy, I only found out this recently, but evidently he gave a TED Talk too, which you can also see, about symmetry. But yeah, he was an Oxford professor. He's a very, very good source. Anyways, right, Professor Coulter has actually a course on geometry and art, actually, which I'll probably link to in the description, by the way. There are some web pages which describe this course, and so he describes Pythagoras as a part of this, naturally. And the main facts of how the Pythagoreans treated music. Basically, they very much liked whole number ratios. So like 3/2 and 4/3, and I think 9/8 is another one. They basically found that these ratios of frequencies lead to sounds that are in harmony with each other and really sound right together. So that's quite good, and that will become important later. In fact, this love of whole number ratios came to be known as Pythagorean tuning, and you can see in many other sources, actually, which I'll link to, that's or at least was a valid and interesting way of viewing sound, basically, in music. Now, specifically, Professor du Sautoy, on the right, he, in his book, described Pythagoras adjusting the volume of water that was in an urn, actually, and adjusting that level to these whole number ratios led to harmony when the bucket was struck, or when the urn was struck, essentially. So according to one story, that's That's at least one experiment that was done in Pythagoras' time. But getting into really the relationship between pitch and frequency, I'd just like to talk about this briefly. Basically, if we, for instance, were to double the frequency of some sound, by the way, frequency is typically treated as hertz, basically. That's the unit of frequency, essentially. And that's what I have as F0 or F1. Just presume we have two different frequencies. And if we take some multiple of 2, as I said before, or double the original, the starting frequency, F0, a certain number of times, so 2 to the n times F0. Just is all I'm trying to say there. It yields a change in an octave, basically. So it makes it an octave higher, or more generally, n octaves higher. So, for instance, we know that the number of hertz for a common A, like the note A, sounds a little something like this. That's about 440 hertz. And if we were to double that, for instance, and get 880 hertz, 880, that would lead to a sound that is basically the one octave up, A, which, at least in this case, would be the A on the E string. So I'm going to try to get that, actually. Versus... But anyways, I just wanted to demonstrate that. What that actually means is that we get an exponential regression, which is what I've graphed here, with help, by the way, from Wolfram Alpha. I very much recommend that source. Basically, computational knowledge engine. You can type in nearly anything into the database that is Wolfram Alpha, and it'll tell you a lot of detail about whatever you ask it for, whether it's population density of some city, probability, or a differential equation, or some sort of graphing of a parabola. Really, it can do pretty much anything. In many cases, it doesn't even have to be related directly to mathematics. Sometimes it can be just like, what is the frequency of this word in the English language? Or what is the definition of some term? It can really be quite useful, but of course for plotting things it's also especially useful. I recommend it for that. But anyways, moving on. So we're getting exponential regression. Sorry, I kind of digressed there, but anything that involves an exponential regression can actually be considered with, you guessed it, logarithms. And of course, you know I love logarithms. I'm sure you probably already know that. But anyways, there are a couple different points I'd like to make. I say other relations here. The frequency of one tone and the frequency of another. It's important to consider the ratio between those two frequencies, and that's a special number, really. And cents are kind of a measurement of difference between, or I should say, a measurement of this ratio. We'll get to more on this use of the word cent, measuring that ratio later. We'll get to that later. Many uses of that and what it really means. But furthermore, we have this circle of fifths down at the bottom, which shows another interesting part of music, and that is the relationship between major and minor scales. And some of you probably already know about that. You can see how adding a sharp or a flat alters the key, basically, in a cyclic fashion. So, basically, B major can be considered the same thing as G sharp minor. D major, in terms of the key, is essentially equivalent to B minor, at least by the key signature. And there's this kind of circular pattern to it. Kind of reminds me of group theory, honestly, which is what I will describe in actually a later video. That's what I expect to make later in the winter. But I just wanted to point to that. For any of you musicians out there, or prospective musicians, you might kind of be fascinated by it. But anyways, what we really were just discussing, as I said, was the Pythagorean tuning. and that's an example of a framework for musical tuning. And another example of this is actually Temperament. Now, I'm getting a bit ahead of myself. Sources like the Michigan Technological Institute, Hyperphysics at Georgia State University, and several other websites describe different temperaments, which are definitions for basically the framework of music, determining the frequencies, the exact frequencies of different notes. So one of these is actually Temperament, and there are others which I will eventually refer to and compare to, but the well-tempered system, as might have been used by Bach, by the way, sounds more pure, according to some sources, in C major than in other keys. So this is one of the ones that is kind of dependent on the key that you use. And I wanted to play you a bit of a sample, which is available online. And so I'll just click that and make sure my volume is raised so that you can hear that. Now, listen closely, because ultimately I'd like to compare these different kinds of musical temperaments, and, well, you'll see where I'm going. That's that temperament. And there are many different kinds of temperaments. There's also this just temperament, actually, which is what we're getting into. And again, it involves whole number ratios, so one could argue that just temperament and Pythagorean tuning, they're very much related. I believe one is, I think, an example of the other, or at least, well, they're very closely related. There might be a technicality that makes them slightly different, but I won't get into that. They involve whole number ratios, similarly, and it's somewhat dependent on the scale that you use, somewhat similar to Temperament. And so I'm gonna play an MP3 sample of actually the same song from before, but now in just temperament. And so again, the spacing of the notes isn't really the same, but now that was just temperament, alternate system, and so nowadays, in the past 100 years or so, we've been using this equal temperament system. And one could argue it's a bit of a compromise. It has new advantages that the others don't. And it relies on, as you can see, this large number here, the 12th root of 2, which is irrational. 1.059463, etc., etc. And so, this is alright. There are certainly many advantages. And basically it distributes the quote-unquote impurity, or the whatever flaw might be found in some of the notes of the other systems, kind of distributes them equally. And we'll probably get to why and how that is later. But just to play you a sample of, again, the same song. I believe this is a G major song. Played in this case, equal temperament. Right, so that was just the sample, and basically the advantages I begin to list here of equal temperament. Basically, it makes transposing music easier, transposing it to a different key, and certainly makes it easier to use different instruments to play the same music. And really, it has grown over the past few hundred years. I believe one source described the really, it was the 20th century when equal temperament became pretty much the standard, really the universal system. And I think Kevin Boone does a good job of describing these different temperaments as well. I encourage you to perhaps look up some of the details. And in fact, Kevin Boone was the one, he's a computer scientist, and he also was the one who listed these MP3 sound files of the differences that I just showed you, basically. The actual clips that I just played. So I was very kind of him to really post them there just for free. And so it's interesting stuff. But in reality, I'm guessing you might be wondering, as many people have wondered, can we actually tell the difference anymore between these temperaments, between these systems? Honestly, I think it's arguable that we are less equipped to tell the differences between these systems, at least in the modern age. Potentially less equipped to really identify the specific differences than, people of the past, particularly musicians of the past. But nonetheless, clearly the access to music in modern day is much greater than it used to be hundreds of years ago. Yes, that's also probably clear. Yeah, I think that's very arguable. Nonetheless, it's just something to think about, just something interesting. In fact, here are the actual numerical differences in pitch that we have. So I know it's a bit of a large table to take in all at once, but this comes from Wikipedia. And we have the name of the tone, and then these different values. And it's essentially comparing equal temperament, or ET, it says there, decimal value in 12 to ET. And that's what the ratio is, actually. As compared to the C, basically. Being the unison. And so it gives a nice list here. Basically, the way cents are set up is that basically there are precisely 100 cents in between each note in equal temperament. So basically they're equally spaced according to this formula for cents, which I described earlier. It's basically 1200 multiplied by the log base 2 of the ratio of frequencies. And you can probably see a kind of a derivation of that on screen now. Basically, we're dividing, at least when considering equal temperament, we're dividing this whole scale into 12 equal subsections. And it's quite interesting. So now we basically want the new frequency. Since we want it to be equally spaced, we want it to be basically a power of the 12th root of 2 times the initial frequency. So that's just where this formula comes from. We want to ensure that we're kind of making a geometric or kind of exponential regression with this. So we take the 12th root of 2, raise it to n, multiply that by the original frequency, and that's how you get the new one, to make sure that it's basically a constant r that we're using. And, cents are defined to be 100n in this equation. And we can verify that 1200 cents are in one entire octave, essentially. So it's divided evenly in that sense. In that sense, they're divided equally into cents. See, it was like a pun. Anyways, in just intonation, we can see in this table right now, we can also calculate the number of cents, since we know the ratio of these two frequencies. So we can apply the same formula, basically, and we get a slightly different number, is basically all you should be drawn to, really. We have this error in this final column, so really some of the frequencies are pretty far off. They're up to like 15 if you look at the minor third. It's minus 15.64 error. For the augmented fourth beat, you can get a 17 point error, or cent error, more accurately. So sometimes these are actually fairly noticeable if you study them mathematically. So the difference between these is supposedly noticeable, but perhaps this is all a lot to take in at first, but it just tells you those differences. Now, if you have any questions, seriously, just let me know. But I might not be doing a perfect job of explaining it, but I just think that's interesting. No, isn't that amazing? Doesn't everyone love logarithms? I just love logarithms. In all seriousness, logarithms are the very basis of cents and decibels. Now, decibels are slightly different. That kind of just describes something else. It's really the kind of loudness of a particular, or amplitude, perhaps is more accurate, of a sound. But still, it's truly interesting, and I promise at some point more is coming on why the natural logarithm, I just say log here, I'm referring to the natural logarithm, is so amazing in and of itself. So please be on the lookout for that. But yes, we have this formula. I alluded to it earlier. We have 1200 times the log base 2 of the frequency ratio. And there are many different sources which you can check out. But yeah, I just wanted to give you at least a bit of an introduction to all these different kinds of musical frameworks. I find them really quite interesting. And, you know, just as some final thoughts, I really wonder in general how many people know about this in the world. I'm not sure I honestly knew. You know, maybe I'm just kind of foolish, but I didn't quite know about these different historical frameworks for music. And this is just nice to study, the development of music. And is it not an interesting topic, I say, that more people should know about? I believe so. But that's just me. And again, this is just part one of this ongoing music and mathematics series. So, have any questions, let me know. And here is my kind of signature or stamp of approval. And so, in all seriousness, happy winter break, happy holidays, and I will see you another time. There are some just works cited and additional sources.